Welcome to Core Apache Beam Transformations for Part 3 of the Dataflow series. This segment is a non-optional video for studying for Google's Professional Data Engineering Certification exam. This means we're going to be covering testable material. You should expect at least one test question on Apache Beam's core transforms. After I introduce a transform, I first discuss its definition, whether or not it accepts a function as an argument, and what exactly it does. Next, I show you what the code looks like in Python code. Now, Java is actually the preferred language of Beam, but I personally find Java outdated and will be showing Python examples. Simply put, more and more data scientists are learning Python, so that's what we're going to stick to for these lessons. Please be aware that there are limitations to Python and Apache Beam, but we'll find ways around them through libraries. After I discuss the transform and show you example code for each one, if I found a test question regarding the transform, I show it next to further instill how Google may test you on this particular concept. Please be aware, just because I didn't find a test question on a core transform does not mean that Google will not have one on your exam. That's why we're going to learn them all. Well, let's get started. If you are following along with the optional second video, then this is material that has already been covered, and feel free to skip to the next concept. However, if you decided to skip that one and just learn what is needed to for the exam, then this will be new information. A P collection is owned by the specific pipeline object for which it is created. Multiple pipelines cannot share a P collection. They may be any data type, but a P collection must all be the same type. P collections do not support random access to individual elements within the P collection. Transforms are applied to every element within the P collection individually. Once a P collection is created, elements cannot be added into or removed. Beam transforms do not change P collections. There is no limit to the number of elements that a P collection can contain. They can be bounded, in which case it contains a finite number of elements, or unbounded, without limit to the number of elements. A timestamp is associated with every element of a P collection. Each element's timestamp is initially assigned by the source that results in the creation of the P collection. Transforms are the operations in your pipeline and provide a generic processing framework. You provide processing logic in the form of a function object, and your user code is applied to each element of an input P collection, or more than one P collection. In Dataflow, many different workers across a cluster may execute instances of your user code in parallel. The user code running on each worker generates the output elements that are ultimately added to the final output P collection that the transform produces. Beam actually has close to 40 different transforms, and I'm not going to be getting into all of them. In this lesson, we will be covering Beam's core transforms, which are the Pardue, group by key, co-group by key, combine, flatten, and partition. Pardue is the Beam transform for generic parallel processing. Pardue accepts a user-defined function, or doFN, which we will be discussing next. A Pardue transform considers each element in the input P collection, performs some processing function, which is defined in your user-defined function, or doFN, on that element, and emits 0, 1, or multiple elements to an output P collection. It is used whenever something needs to happen to every element. Examples of when to use Pardue include to filter a dataset, to perform format or type conversion, when we need to extract parts of each element, or performing computations on each element in a dataset. In the example, our input P collection contains string values. We apply a Pardue transform that specifies a function, in this case, compute word length, to compute the length of each string and outputs the result to a new P collection of integer values that stores the length of each word. All right, let's look at an example test question for the Pardue transform. You are creating a new pipeline in Google Cloud to stream IoT data from Cloud PubSub through Cloud Dataflow to BigQuery. While previewing the data, you notice that roughly 2% of the data appears to be corrupt. You need to modify the cloud Dataflow pipeline to filter out this new corrupt data. What should you do? All right, so what are some key details here that might help us? We did just learn that the Pardue transform can be used to consider each element in a P collection and to either output that element in a new collection or to discard it. And that it can be used to filter out data. So our answer is to add a Pardue transform in the cloud data flow to discard corrupt elements. The doFn object that you pass to a Pardue contains the processing logic that gets applied to the elements in the input collection. When you use Beam, often the most important pieces of code that you'll write are these user-defined functions. They're what define the pipeline's exact data processing tasks. Inside your doFn subclass, you'll write a method process where you provide the actual processing logic, and typically this is actually called processing or process. You don't need to manually extract the elements from the input collection. The Beam SDKs handle that for you. Your process method should accept an argument element, and you'll usually see it called element, but sometimes they're called something else, but typically they are called element, which is the input element, and returns an iterable with its output values. In this example, we've defined our user function as a class. Here, we will always pass in beam.doFn to tell Beam that we're using a user-defined function. Next, we define the process as a subclass and pass in the required arguments of self and element. Remember that this is the input element that's required to use a doFn. Please note that sometimes these input elements are defined before the user function class is, and in that case, the name of the element will be passed instead of the arbitrary term element. Next, we need to return an iterable, since it is something that is done to every element in a P collection with its output values. So here's an example of a test question for the doFn. You need to ingest streaming and batch data into BigQuery, but each row must be annotated with a unique identifier that is created by a third-party HTTP system. What is the best way to achieve this? All right, so what are some key details about this question that could help us answer it? Well, we know that since we need to ingest streaming and batch data into BigQuery, that the product that we need to select is Dataflow. We know that each row needs to be annotated with a unique identifier through an external HTTP. This means that we're going to be making an HTTP GET request, and the best way to do that is with a user-defined function. So the answer here is create a doFn function in Cloud Dataflow that calls out to the external HTTP service for the unique identifier. In addition to the main input P collection, you can provide additional inputs to a Pardue transform in the form of side inputs. A side input is an additional input that your doFn can access each time it processes an element in the input P collection. When you specify a side input, you create a view of some other data that can be read from within the Pardue transform's doFn while processing each element. Side inputs are useful if your Pardue needs to inject additional data when processing each element in the input P collection, but the additional data needs to be determined at runtime and not hard-coded. Side inputs are passed as arguments to your doFn processing phase, or map or flat maps callable. All right, let's look at an example. So here we've defined our input P collection words. We've defined our class filter using length and passed in the required doFn argument. During the processing method, we passed in our usual arguments of self and element. But as you can see, we passed two additional arguments, and these are our side inputs. We're returning the elements that meet the condition that the element is between the two bounds that must be provided during the function call. We're using this to filter out elements of a specific size. Within our pipeline, we've defined our output P collection small words. The doFn filter using length is passed to the Pardue transform to our input P collection words. Since we have two additional side inputs, we need to provide the two integers after the function call. This will return the words that are between the bounds that have been specified. In this case, it will return the words that are 3 words and under. Pay close attention to how this is formatted. The integers are not passed as inputs to the user-defined function. Instead, they are passed to the pardo function after the doFN function call. Let's look at an example test question for side inputs. You are writing a streaming cloud Dataflow pipeline that transforms user activity updates before writing them to a time series database. While continuously transforming each element as it arrives, you also need to depend on some additional data at runtime to create the transformation. How can you achieve this? So what are some key details that can help us answer this question? While continuously transforming each element as it arrives, this means that we can use the pardo function to achieve this. You need to depend on some additional data at runtime. Both the additional data and the fact that it's implemented at the runtime tells us that this needs to be a side input. So our answer is provide the additional data view as a side input to the transforming pardo function. Aggregation transform is a process of computing a single value from multiple input elements. In Apache Beam, this normally means aggregating across all elements with a common key and with a common window. User-defined functions can be used in aggregation transforms. Beam has several aggregation transforms, but we will be focusing on 2 of them for the test, and they are group by key and co-group by key. Group by key transform is used for processing collections of key value pairs, used to collect all the values associated with a unique key. Our input is a P collection of key value pairs where each word is a key, and the value is a line number in the file where the word appears. Here's a list of key value pairs in the input collection. So in this example, we have cat, there's 1 cat, there's 5 dogs, etc. Group by key gathers up all the values with the same key and outputs a new pair consisting of unique keys and collections of all the values that were associated with the key in the input collection. If we apply group by key to our input collection above, the output collection would look like this. See, we've grouped all of our multiples together. The co-group by key is used when combining multiple key collections. It performs a relational join of 2 or more key value P collections where they have the same key type. In the illustrated example, the pipeline reads names and addresses from a database table and reads names and order numbers from a Kafka topic. The pipeline then uses co-group by key to join this information, where the key is the name and the resulting P collection contains all the combinations of names, addresses, and orders. I'm actually going to do a pretty long explanation for this code. If you can read this and understand everything that's going on, feel free to skip my explanation, especially if you watch the second video, which is using Beam. Otherwise, pay attention. So we've imported our library as we should always do first. Then we started our pipeline. Don't forget that the format is output P collection equals the initial input P collection. So our output is icon pairs and duration pairs. These will be our values later, while our input P collections are icons and durations. These will be our keys later. We first create an input P collection icons using the beam.create method, passing a list of tuples using a key value pair pattern. Next, we create a second input P collection duration, passing another list of tuples with the same keys but different values. Notice that both tuples have the same key type. In this case, the produce name. Since co-group by key expects a dictionary of named key P collections and produces elements joined by their keys, we create a new dictionary named plants with 2 keys, icons and durations, with their values of the output P collections. Finally, we merge the 2 using co-group by key to perform a relational join of our key value P collections where they have the same key type, in this case, the produce name. The values of each output element are dictionaries, where the names correspond to the input dictionary with lists of all the values found for that key. Let's look at an example test question for co-group by key. You need to design a pipeline that can ingest batch data from your organization's application metrics as well as your user database. Then join the data using a common key before outputting to BigQuery. What is the most efficient way to go about this? Okay, so what are some key details here that's going to help us answer the question? Well, it says that we needed to design a pipeline, which means we need Dataflow. It says to ingest batch data from your application as well as your user database. Now this tells us that we have two sources and that it says to join the data using a common key before outputting to BigQuery. Now obviously that's our biggest clue of all, that we're joining two sources using a common key. So that means that we need co-group by key. And our answer is create a cloud data flow pipeline and join the two P collections using co-group by key transform on the common key. That was pretty easy. The combine transform is a beam transform for combining elements. Pre-built functions include sum, min, and max. Combine requires you to provide a function that defines the logic for combining elements. Combine has variants that work on entire P collections and some that combine the values for each key in P collections of key value pairs. Combine globally works on the entire P collection. Combine per key combines the values for each key in a P collection of key values. Combine per key accepts a function that takes a list of values as an input and combines them for each key. Combine globally accepts a function and takes an iterable of elements as an input and combines them to return a single element. Let's look at the code. After importing the libraries, we define a function, getCommonItems, which takes an iterable of sets as an input and calculates the intersection, common items, of those sets. Set.intersection takes multiple sets as separate arguments. We unpack the sets list into multiple arguments with the asterisk operator. The combined transform might give us an empty list of sets, so we use a list with an empty set as a default value. Within the pipeline, we name our output P collection common items. Then we create an input P collection produce. And then we apply combine globally to combine all of our common items into a single new P collection. The flattened transform merges multiple P collections objects into a single logical P collection. You can use the flattened transform to merge multiple P collections of the same type. The following illustration is an example of a pipeline that merges two P collections into one P collection with the flattened transform. In this example, the Pardue transform has output two P collections from a database of names, A names and B names. The flattened transform merges the two P collections into a single P collection, A and B names. All right, let's look at flattened transform example code. Inside our pipeline, we set our output P collections as words starting with A and words starting with B. We've created our input P collections and passed in a list using the beam.create method. Next, we pipe both input P collections directly into the flattened transform method. Now, alternatively, we could have created a new output P collection called words starting with A and B to equal a tuple of both input P collections. But either method will still result in a single P collection that contains all the elements in the P collection object. All right, let's look at a test question example of flattened transform. You want to update a cloud Dataflow pipeline to use the same P transform on two P collections, which are both the same type CSV row data. What is the best way to achieve this? All right, so what are some key details in this question that might help us answer it? Both P collections are of the same type, making it a prime candidate to use the flattened transform. So our answer is use a flattened transform on the P collection to merge them prior to the P transform. Partition is a beam transform for P collection objects that store the same data type. Partition splits a single P collection into a fixed number of smaller collections. Partition divides the elements of a P collection according to a partitioning function that you provide. The partitioning function contains the logic that determines how to split up the elements of the input. Before we begin, it is useful to note that partitioning accepts a function that receives the number of partitions and returns the index of the desired partition for the element. The number of partitions passed must be a positive integer, and it must return an integer in the range 0 to number of partitions minus 1. With those rules in mind, let's take a look at the code. This particular example divides a P collection into percentile groups. We start with our input P collection variable students. We've defined a function called partition function, which takes 2 arguments, but the first argument, student, is the element, while the second argument is the number of partitions. Both are required to apply the beam partition transform. In the return section of our function, we define the logic of how we would like the partition transform to split up the P collection. Inside the pipeline options, we will provide an integer value that represents the number of result partitions and a partitioning function, which we've defined above. This will return a tuple of P collection objects containing each of the resulting partitions as individual P collection objects. In this way, we have split up our single P collection students into a fixed number of smaller collections. We've covered a lot in this video, and it's actually twice as long as the other videos. But some of the transforms had example test questions, so what notes from them might be useful? So the PAR-DO is a generic parallel processing that can be used to consider each element in a P collection and either output that element to a new collection or to discard it. We looked at the DoFN, or the user-defined function. You'll write a method process where you provide the actual processing logic. We looked at side inputs, which require additional data at runtime. We looked at the co-group by key, which is joining the data using a common key. And we also looked at the flatten transform, which is merging the same type of data. This completes the third lesson on Dataflow, which covered Apache Beam's core transforms. Join me on the next lesson where I will be covering Apache Beam's advanced topics.